Okay, we thank Alessandro for the very nice introduction, and now talk to Giorgi to give his version.
So thank you, Alessandro, for that great introduction, covering many topics that I now don't have to cover. Thank you everyone for being here, either if you're here or remotely, wherever in the world you may be. So I'm here defending my thesis today, astrophysical impacts on habitable planetary systems that I've been working on for the past 5 or so years. So let's jump right into it. We already went through the errata, and let's also go through some stuff that's not really in the thesis. So the thesis is about, in a way it's about extraterrestrial life, but also not really. Either way, this is a topic that's very interesting to our imagination. So the first paper that we published ended up being the paper of the month according to Science, which was a nice little thing to have tagged on the paper. And for the second paper, I gave an interview to a New Scientist, which resulted in this article here shown. And additionally, I co-authored another paper that was not included in the thesis, which used the results from our first paper to try to explain the existence of Uma, I think that's how it's pronounced, this asteroid or comet that passed through the solar system that may have been formed in another solar system. So the work in this thesis covers 3 papers. Let's start with the second paper. So the second paper is the last thing that Alessandro mentioned. It's about the initial architecture of the system and how that affects said system's long-term habitability. And then the third paper is about what happens after the system is formed if it encounters other stars, usually in its birth cluster. What can happen to this system? And then in the first paper, we look at systems that make it out unscathed from the birth cluster and start orbiting the galaxy on their own, and what could happen to life in these systems. Make an analogy to life here on Earth, we could use paper 2 as maybe the genetics of a person, paper 3, the family or the neighborhood they're born in, and the first paper then where in the world they're born. This will affect how life develops for the person. It's a similar analogy, I think. But let's jump into paper 2. So if we were to define it as one question in this paper, it's given observed planets in the system, can there be a planet in the habitable zone? And what we find is that it really depends on what we can say about the history of the system. If these observed planets give an indication of there having been a planet-planet instability resulting in scattering, this would be very destructive to the habitable zone. And this was explored by a previous student here, specifically for the solar system, Daniel Carrera, whereas we look at nearby exoplanet systems in more detail. And the concept in this paper main concept is the so-called resilient habitability, and that is the fraction of the habitable planet orbits that survive the dynamical evolution of the system still inside the habitable zone. So let's look at what happens when planets scatter and why it can be so destructive. So when planets form very closely, like you see in the leftmost image here, they will exchange a little bit of energy. And this exchange of energy can eventually lead to them getting so close that their orbits cross over. And once the orbits cross over, well, then one of these two planets are pretty much done for. Because if they start getting close enough to directly scatter, they will keep doing so until one of them is removed and the other one is left on an eccentric orbit. And what we can see here is that during this scattering, the orbits of the planets will change. And in this process, the system itself can be much more destructive to the habitable zone, seen in green here, than how the system is afterwards, when you're left with a single planet on an eccentric orbit. So we looked at some nearby planetary systems, and we saw that most of the observed giants nearby show a sign of eccentricity. So we postulate that, okay, what if all of this eccentricity came from planet-planet scattering? And in fact, you can actually reproduce the eccentricity distribution pretty well under that assumption, but we took it, what we did in particular was to assume that the scattering either happened with an equal mass planet or a planet a third of the mass of the observed planet. So it's either equal mass or a third of the mass. And you can see here in the top figure the resulting eccentricities of when you scatter a Jupiter-Jupiter or a Jupiter-Saturn. And you see it covers the entire span of eccentricities. So for the observed systems, we assumed that it started off either with an extra Saturn in the system or an extra Jupiter, with equal mass or a third of the mass planet. And then we simulated them. And the systems we simulated are shown in black on the bottom figure. And what we find is, well, here's a subset of the systems that we simulated. And if we first simulated them in their present state and checked what fraction of the planets in the habitable zone remain in the habitable zone, and you can see that distribution as black on the right-hand figure, whereas the left-hand figure shows how the planets look now, and the corresponding survival rate in the habitable zone, which is the green part of the figure, is the black line. Now, if we assume some sort of dynamical history of these systems, what we see is the orange distribution. So we see here that when the history of the system is considered, nearly in every single case, a much smaller fraction of the habitable zone remains habitable throughout the process. And yeah, that was the main finding of this paper. So in the third paper, title's in here, if we boil that down to a question, is what happens to a planet in the habitable zone when a massive planet is captured on a wide orbit? So close encounters between two stars have been shown to be able to destabilize the planets orbiting each star. And if this destabilization happens, we're essentially back to the previous paper that I discussed. Same sort of effect, but an external perturber. However, during such encounters, a planet can actually be exchanged to the other system. And we wanted to see what happens during such an exchange. And these encounters often happen, most often happen in birth clusters where the stellar density can be 1,000 times higher than what we see in the galactic field. So we did the experiment where we set up a simple system, a sun and Earth, a Jupiter at 10 AU, an asteroid belt, and an inclined companion, which is sort of the captured companion. And this captured companion will often be inclined. And what can happen with an inclined planet, or to inclined bodies, or if you have a system with an inclined body, what can happen is that it can transfer some of its angular momentum to other bodies in the system through so-called Kokaia cycles, where they will exchange angular momentum, inclination will go down, and eccentricity will go up. And the asteroids here are very vulnerable to this, so the eccentricity will increase sharply and they will be pushed in to the orbit of the Jupiter. And we can see what happens as a flowchart, really. So if you start with an asteroid belt, they will have their eccentricities excited. And what can happen then is that they will encounter the Jupiter, which can either eject them or knock them into the system. When they knock into the system, they might be knocked all the way into the star. They might end up being ejected, but a small subset of them will actually end up hitting the Earth. And what we find is that about 4 in a million asteroids will end up hitting the Earth. If you consider the current Kuiper belt, that will be about 40,000 kilometer-sized bodies hitting the Earth if the whole belt is disrupted. But this 4 in a million appeared to be pretty constant regardless of what simulation we did. So we could work with this assumption and then just do a bunch of low resolution simulations to see how many asteroids are removed for companions captured on different orbits. So we do a bunch of simulations with companions on different orbits, and then we have a few points which we know what the impact rate would be and so forth. And then we can draw random companions on random inclinations and eccentricities and just interpolate between these points to get sort of a generalized outcome of what would happen. And if we look at the outcome space, we see that about 40% of the systems just end up being destabilized when they capture a companion. Either the companion's orbit will just mess up the planets, or it will actually collide the planets into each other and just mess up the system. But when it doesn't, we see outcomes grouped in 3 ways pretty much. We get a very high burst of comet. Sorry, in this figure here, on the x-axis, you see for how long the bombardment lasts of asteroids on the Earth, and on the y-axis you see by how much the bombardment rate increases compared to the baseline measured on Earth. So there's basically 3 outcomes. A very high burst for a short amount of time, which for an astronomer is a few million years. A medium burst for a medium time, which is a few tens of millions of years, maybe 500 million years, or a low rate for a very long time. The first 2 are actually not that bad for the system, because these captures are most likely to happen in the birth cluster. And in the birth cluster, while you're in there, the habitable planet is still essentially a ball of magma. So if that gets bombarded by a bunch of asteroids, not much is going to happen. But in the last case, you can get this companion that sticks around and raises the impact rate on the system for 1 billion years or more, up to a factor of 10 higher than what we see on the Earth. And life wouldn't be very happy evolving on a planet like that. And then finally, the paper 1 then actually, where we talk about how the location in the galaxy matters. Well, here we ask the question, how often do stars go through or hit giant molecular clouds, which was mentioned by Alessandro. And GMCs are these large and dense gas clouds, and they're located primarily in the spiral arms. So when a star goes through a spiral arm, it's likely to also encounter GMC. So we created a galaxy model here, which is shown in the figure, where in which we can simulate stellar orbits and see how often they go through GMCs. And what we find is that it's a sharp dependence on both the radius, which is the color code here in the figure, and what we call the VZ, which is the velocity away from the galactic plane. This VZ is actually a proxy for the age of the star. The older it gets, the higher its VZ gets. So if you consider young stars at smaller radii, like 5 kiloparsecs, they can have 100 or more encounters in a gigayear, whereas older ones by the solar circle will have maybe 2 or 3. And why does this matter? Well, it was touched upon by Alessandro, but say the planet gets out unscathed from the star and the planet gets out unscathed from the birth cluster. Life hopefully evolves on this planet, but life can still be extinguished by stuff from space. And we know that because that's what happened to the dinosaurs. And that's really the only mass extinction where we actually know the cause for sure. And we believe that that passing through a GMC can potentially cause a mass extinction. Primarily in one of 2 ways, and that is that stars actually form inside of GMCs, and stars that end their life as a supernova are short-lived. Once again, short-lived for an astronomer, a few millions, tens of millions of years, so they don't really have time to leave the GMC before they explode. So when you're in there, you're likely to be blasted by a supernova. And it's not necessarily the blast that kills the life on the planet, rather it's a few complicated processes that can occur. We don't really know exactly which, but the 2 leading theories is that nitric oxide formation in the upper atmosphere due to the cosmic rays will lead to the ozone layer being destroyed. And as the ozone layer is destroyed, your host star slowly but surely gives you cancer and kills you. Or this bombardment of high energy particles actually seeds cloud formation. And when you get a bunch of clouds, you end up reflecting more light. This cools the planet, which creates larger ice caps, which reflect more light, which further cools the planet, and you get a runaway effect, leading to an ice age, a snowballing effect, leading to an ice age known as the snowball Earth. And this is actually the same thing that can happen simply because of the gas in the GMC, because as the star passes through this gas, a bunch of gas can be gravitationally focused on the star and the planet. This gas brings with it dust. The dust settles in the upper atmosphere. Cloud formation, same process. So these historical mass extinctions that we know of, other than the dinosaurs, might have been the result of either of these 2 processes. And we considered that, but we essentially concluded that it's quite unlikely, because when we simulate the sun in particular, here we see a distribution of outcomes for for the sun's orbit, and we see that it will encounter GMC about once per 700 million years, and a supernova about half as often as that. Further, the accretion rates really are too low to cause a snowball situation, so we don't really think that, given the sun as it is now, that it would have that it can explain the fossil record. However, there is some observational evidence pointing toward the sun forming at 5 kiloparsecs rather than the 8 where it is now. In that case, and was young, the encounter rate could have been 100 times higher. So that would change things. So it could be quite different in the past. So if we look at the summary and answer to these questions that I gave, given an observed planet, can there be planet in the habitable zone? Well, for close-in and eccentric planets, no. But otherwise, yeah, most of the time it's possible. And then what happens to a planet when a massive planet is captured on a wide orbit? Well, 40% of the time this capture just messes up the whole system. 40% of the time you get a very high impact rate that passes quickly, and 20% of the time you get like this slow and steady silent killer, so to speak, that just makes it very hard for life to evolve on the planet. And finally, well, how often do stars hit giant molecular clouds? Well, about once per gigayear or so. And for for a star like the sun, that is. But younger stars further in, the rates can be 100 times higher, which is, yeah, very different. So, thank you all for listening.
Thank you very much, Giorgi. So now it's time for the opponents to ask questions to Giorgi, and I guess I will just leave you here.